So the second section of FreeResponse are ones that you'll be given a chart. And these are on every AP exam. Some of them are calculator active, some aren't. But they're usually, once you get the hang of it, some of the easiest that you should be able to get all the A and B, probably most of the C, and some of the D. So let's look at this first one. You can read the problem in your notebook. It's the 2012 one. It says, use the data in the table to estimate the derivative at 12. Show the computation that lead to your answer, use correct units, and interpret the meaning in the problem. So anytime they ask you to estimate and they got a table, you're going to use your slope formula. So 12 is going to fall between the 15 and the 9. So we're going to do W of 15 minus W of 9 over 15 minus 9. And if you work that out, it's going to be 1.017. And of course, you can see it's Fahrenheit over minutes. You get 1 point for just writing that unit, even if you got everything else wrong. So remember your units. And it's the rate that the water is increasing at the time 12 hours. So, and you can tell how to describe this because it's going to tell you what the rate's representing. And of course, it's at 12 hours, and because it's positive, the rate's increasing. So part B, use the data in the table to evaluate the integral of 0 to 20 of WT D of T. Use correct units, interpret the meaning. Okay, so again, on all of these type problems, when you have an integral of the derivative, remember they're inverse operations of each other. So that is just W of 20 minus W of 0. And we don't have a function rule, so we get those values right from the chart. So it'll be 71 minus 55, which is 16 degrees Fahrenheit. And this is what the water has warmed to over the interval from 0 to 20 minutes. Now, part C, from 0 to 20, the average temperature of the water is 120, 0 to 20 of WT. Use a left Riemann sum with 4 sub-intervals indicated by the data in the table to approximate this value. Does this approximate an overestimate or an underestimate of the average temperature of the water? Explain your reasoning. Okay, so remember when we did sums and we drew little rectangles? Well, in a chart, you're just going to do, so you've got 4 sub-intervals. So you've got 1, 2, 3, 4. So remember the width is the difference in the x values. And the left sum obviously will be the left entry. So you're going to have 4 times 55, because that's the left one for that interval. And then from the interval from 4 to 9, that width is 5, and the left value is 57. And then from the interval 9 to 15, the width is 6, and the left entry is 61.8. And the interval from 15 to 20, the width is 5, and the left entry is 67.9. Now, you're going to add all that up and multiply by 1 over 20, because remember it said average value. And if you get that, you get 60.79. Now, this is an increasing function, so remember if it's an increasing function, the left will be an underestimate because it's on the lower side. So part D, for 20 to 25, the function W models the water temperature, the first derivative given by WT equal 0.4 square root of T cosine of 0.06T. Based on the model, what is the temperature of the water at time equal 25? Okay, so this is starting after you had gotten through your table. So you're going to take that initial value being 71, and you're going to go from 20 to 25 of the derivative of WT. And that's going to equal your W of 25. And so here you can just use your Math 9, type this in your calculator because you have a function rule, and you'll get your answer of 73 degrees Fahrenheit. So let's look at the 2011 one. If you read this in your book, it's talking about T cooling, temperatures in Celsius, and times in minutes. So part A says, use the data in the table to approximate the rate at which the temperature of the T is changing at T equal 3.5. Show your computation. So again, if you look down here at A, we're going to approximate. So it falls between 5 and 2. So h of 5 minus h of 2 over 5 minus 2, and you get negative 2.667. Part B says, using the correct units, explain the meaning of 1/10, 0 to 10 h of t in the context of the problem. Use a trapezoid sum with the 4 subintervals. And your trapezoid formula is 1/2 h, b1, b2. So h is going to be your difference in your x values. So if you come down here, you can put 1/10 because of the average, 1/2 because of the trapezoid formula. And then your first interval is a height of 2, and then you take your 2 bases. The next interval, it's a height of 3, and your 2 bases. Next one's 4, your 2 bases. Next one, 1's your 2 bases. And if you add all that together, you get 52.95. And that's the average temperature of the T in Celsius in 10 minutes. So part C says evaluate 0 to 10 h, the derivative of h of t. Use correct units. And again, remember when you take the integral of a derivative, they're inverse operations, so you just go h of 10 minus h of 0 straight from your table. That's negative 23, and that's the temperature drop in Celsius from 0 to 10 minutes. So part D says, at T equals 0, biscuits with a temperature of 100 degrees were removed from the oven. The temperature of the biscuits is modeled by the function B of T. Use the given model at time T equal 10 to see how much cooler are the biscuits than the T. So we know what the temperature of the T at 10 is, 43. So we need to get B of 10. So what we do is we start with the temperature of the biscuits as 100 from 0 to 10 of B prime T. Now this one we have a function rule, so we can just use Math 9 and get 34.183. So if you subtract that from the T, the biscuits are 8.817 degrees Celsius cooler. So let's look at the next one. This is the 2011 Form B. You've got a chart with the time, B of T, and V of T. And so it's talking about Ben riding a bicycle. B models Ben's position. So this is the position function, and this is the velocity function. Part A says, use the data in the table to approximate Ben's acceleration at t equal 5 seconds. Indicate units of measure. So remember, acceleration is the first derivative of velocity. So when you use your slope formula, you're going to use the velocity. So you're going to say V of 10 minus V of 0, and you're going to get 0.03 meters per second squared. And that's because you've got meters per seconds over seconds. So that's seconds squared. So part B says, using the correct units, interpret the meaning of 0 to 60 of the absolute value of V of t. Approximate this using a left Riemann sum with subintervals indicated by the data in the table. Okay, so remember the absolute value of velocity is distance. So this is going to represent the total distance in meters traveled from 0 to 60 seconds. So again, we're going to have 3 subintervals, and so our width or height, whichever way you want to call it, is 10, and our left in velocity, remember we're in velocity, is 2. And then our next interval from 10 to 40 is 30, and our left interval is 2.6 2.3, and our last one is 20, and our left is 2.5, so that's 139 meters. So part C, from 40 to 60, must there be a time when there's a velocity is 2 meters per second? Justify your answer. Now, this is by mean value theorem, and there are two important theorems that I wait to this time to go over because they really just fall into these free response. And one of them is the mean value theorem. And the mean value theorem says that you have a derivative that will be equal to your slope formula somewhere in your interval. So if you think about velocity is the first derivative of position. So if I go b of 60 minus b of 40, I'm going to get 49 minus 9, and that is going to be 2. So there is a position up there by the mean value theorem that will equal 2. Now, if you were trying to look for that, you know you wanted it to equal 2, so you would just look where the values would be so that you could get to and pick those 2 points. All right, part D. Now, this one is some algebra involved, and again, you're not going to get all the D's, but I think once you see it, maybe you can start thinking outside the box. It says a light is directly above the western end of the track. Ben rides so that the distance L of t between Ben and the light satisfies this equation. At what rate is the distance between Ben and the light changing at t equal 40? So we have to get a derivative of L of t. So that's what we've got to do. So you see right here, I've written out the equation. So if I take the derivative, I'm going to do chain rule. So I'm going to say 2 times L of t times the derivative of L of t. So that's just using the chain rule on that side. And then the derivative of 12 squared is 0. And the derivative of bt squared, using the chain rule again, is 2 b of t, b prime of t, the derivative. So then I'm just going to solve for L prime of t, or the derivative. So I'm going to divide this over. So my 2's are going to cancel out. Now I'm going to fill in my time, b of 40, b prime of 40, and L of 40. Well, b of 40 and b prime of 40 I can get from up here because b prime is velocity. So that comes straight from my table. But how do I get L of 40? Well, I'm going to come back up here, and I hope you can see it down here. Maybe you can zoom in. I go back to my original equation where LT squared equal 12 squared plus BT squared. So if I take the square root of both sides and plug in 40 for T, I get L of T equal the square root of 144 plus B of 40 squared, which is 81, which is 15. Because that's 9 squared is 81. Square root of that is 15. So L of 40 is 15. So I come back in 9, 2.5 over 15, and I get 1.5 meters per second. So that part D was really just manipulating the algebra and knowing the actual chain rules.